All right, so today we're going to talk about two theorems, the mean value theorem and the extreme value theorem. We talked yesterday about Rolle's theorem, okay? And if we just go back to Rolle's theorem and take a quick peek at Rolle's theorem, this is what Rolle's theorem was all about. And this is very important for the mean value theorem, actually. This is where the mean value theorem kind of comes from. Yeah, I think this was maybe first. I can't really tell you about that, but Rolle's theorem is a form of what we're going to be studying today. So remember, if f of a equals f of b and they both equal 0, that is, there's two intercepts here. And this is a continuous function in between. There will be at least one point that has a derivative of 0 or a tangent line that is horizontal. Okay, so no matter what, if I do whatever I want between these two, there's at least one point, and here there's many, where there's a maximum or a minimum or something like that, right? So no matter what I do, how I connect these 2 points, that's a rule. Somewhere at least once. Now, if we extend this, okay, this is where the mean value theorem comes in. And the mean value theorem connects average rate of change, okay, so we're talking about a trip or something, the average rate of change, with the instantaneous rate of change. And that is the speed or the velocity at an instant, let's say, right? So, or the derivative. So this is the connection, the mean value theorem. Now, what I want to do is I want to show you, again, I want to show you Rolle's theorem here. So there's two intercepts. And we have some kind of function here where I have at least one local max or min that has a tangent that is also a slope of 0. Okay? Now, consider this. In Rolle's theorem, what is the slope between the beginning point here and the end point of this interval? Let's say it's a to b. Well, the slope of the line connecting a and b, if they're both intercepts, the slope, yeah, it's f of a minus, that's right, okay, let's do that. F of b minus f of a, actually, over b minus a. Okay, that's the slope of the line connecting a and b. And this would be your average rate of change over this interval a to b. Okay, so we're going a comma b. All right. So the slope here is 0, right? So Rolle's theorem says that there must be at least one value c, and here there looks like there's two, at least one value c where the slope is also equal to 0. Okay, so the tangent f prime at c is equal to 0. That's what that's saying. That's Rolle's. Mean value theorem, okay, does not restrict the f of a and f of b to be equaling 0. They can be whatever they want. So watch this. If I just change this slightly, well, I guess I'm going to have to erase the whole thing. All right, now watch this. So here's my graph. And let's say that I have a graph that looks like this. And here is A, and here is B. Okay, I'm going to have to bring this down a little bit. So f of A does not equal f of B, but here is, let's say this is f of A, right, the first y value. And here's f of B. Now, if we consider this, the slope of the line that contains f of A and f of B, then I get this it's called a secant line to the curve, right? That. Now that slope is not 0 in this case. It's not 0. But it is some slope equaling, let's just let it equal m, okay? Or m1, okay? Or just m. So we have some slope there. And if this was a trip that you were walking or running or driving or something, and this was your speed, okay, distance over time or whatever, between A and B, you would have an average speed. That would be the slope of this line connecting beginning and end point. Got it? Now, the mean value theorem says that at somewhere, at least one place in this interval A to B, there must be a value, or there must be a point on the curve that has the exact same slope as the average slope. So the instantaneous rate of change at some point must be the same as the average rate of change, where this also equals m. Okay, so you see how it's very close to Rolle's theorem, right? So here's Rolle's theorem. Here's a slope of 0. There's got to be somewhere that has a slope of 0. Now, here's a slope of x, or m. There has to be somewhere here that has the same slope, if the function is continuous. Okay, and that's the bottom line there. Mean value theorem, that's what it says. So this is the average rate of change. So there must be a value c, okay, where f prime of c equals the average rate of change. So yeah, so this first part is the slope of the secant line connecting f of a and f of b, right? So, and this c value here is somewhere between a and b. Okay, so there's c. So this is the slope of the secant line. Obviously, this is the slope of the tangent, right? Slope of tangent line. Okay, they have to be the same. They don't have to equal 0. They can equal 0, but they don't have to. They just have to be the same slope. And this is true. And the criteria, or the hypotheses criteria that have to be met, I'm going to talk about here next. Okay? So hypothesis 1. And this is how we talk in terms of theorems. Is the hypothesis or the hypotheses, are they met in this situation? Then we can apply the theorem. So when you're doing your AP exam, all right, use the appropriate theorem to find blah, 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 okay? You must remember, are you hearing me? Listen now, you must remember that you must state that the hypotheses of that theorem that you're going to be using are met. If you do not clearly state that they're met, you lose marks, big time. So you can't just assume, all right? You're going to say, because f of x is continuous, and because the second hypothesis, f of x is differentiable on the open interval AB. So write these two hypotheses down, please, because these criteria have to be met in order to use mean value theorem. The continuous one maybe is pretty obvious. We talked about intermediate value theorem. We talked about Rolle's theorem. We talked about continuous functions and all that. That's important. If there's any jumps or gaps, you cannot use this theorem to prove this stuff. But this one maybe is a little bit different, okay? Differentiable. We talked about this at the end of the lesson again yesterday, what is differentiable. But f has to be continuous and f has to be differentiable. Why? Because, of course, we're talking about f prime of c, right? F prime of c. So we're talking about a derivative. So functions over this interval of a to b has to be differentiable. So it cannot have a cusp like this. It cannot have a corner. It can't have a gap. And it can't have an asymptote, vertical asymptote, right? It can't have any of these situations. None of these are any good. If that could be the case over this interval, then you cannot invoke this theorem, okay? All right. Now here's another question I get asked. Why the open brackets here? Why the open brackets? If you recall, actually, does anyone know why they're not closed brackets? Okay, here's A and B. Let me fill you in. Here's A and B. You cannot have a derivative at an endpoint. It's not possible. You can't. Because watch this. If I were to zoom in on this really, okay, I'm going to zoom in as much as I can. Well, it's going to get haywire here, but watch this. So I see that there is a derivative here. Why? Because this tangent line is below f of x on this side, and it's below f of x on this side, and it touches at one point. That's kind of like the definition of a derivative. If you think about the limits, right? The left-hand limit here coming towards, and the right-hand limit coming towards from the other way, they have to agree, and so this has to be continuous. Well, at an end point, I don't really know if this is truly the tangent, or if this is truly the tangent, or this, or this. Why? Because there is no graph to tell me, over here. I don't know if it's coming like this. I don't know if it's coming like this. You know what I mean? I don't know if it's pretty flat here. So I don't know what the derivative is because we don't have any idea what's happening on the other side. So the endpoint cannot have a derivative. It's not differentiable at an endpoint. And so, of course, we have to write that hypothesis with open brackets because we cannot include A and B in this statement. Okay? It might seem like a little thing, and I would probably say, yeah, it's maybe a little bit of a little thing, but do you need to understand that? Absolutely, you need to understand that. Okay? So we cannot have a derivative at an endpoint. It has to be in a part of the function where there's function to the left and function to the right. Then we're good to go. So as long as the derivative is possible and it's continuous, then we can invoke the theorem. Yeah, question?
So open brackets mean that like it doesn't
Means not including technically A and not including technically B. Yeah, it's everything leading up to A and everything leading up to B. So if I include everything leading up to A, that means that at least A is on the other side of that or whatever. So you can have a derivative anywhere in before B and just after A. Yeah. Okay, so here's the theorem really, and we've already got this written out, and we should know that B and A are endpoints, and C. So this is another thing you probably should write down here, that C is between A and B. Can't be included in there, but C has to be between A and B. And therefore f of C would have to be between f of A and f of B. And that's sort of taken care of course, with this on the interval. But just make sure you don't forget that. Exists number C in the interval A to B. So that's what this means. C is between A and B. F of C is between f of A and f of B. Okay? So let's figure this out. Let's do an example with this theorem. And we'll take it from scratch here. So at what point on y equals x cubed and on the interval 0 to 3 is the slope of the tangent line equal to the slope of the secant line connecting f of 0 and f of 3? So take a moment to jot that down if you need to. We're going to keep in mind our formula, and of course we're going to make sure that our hypotheses 1 and hypotheses 2 are met. Okay, so that's good. Just for clarification, secant line touches a graph more than once, and tangent line touches just once. All right, so if we sketch this out, we can kind of see a little bit more clearly. X cubed kind of looks like this, right? That's what your x cubed looks like. Now, it's a polynomial function, so it is continuous. Okay, it's continuous polynomial function. It is differentiable. On the open interval 0 to 3. So because there's no gaps, there's no discontinuities, again, you could cite because it's a polynomial function. Okay, polynomial functions where you have the x's and just, whole number exponents, right? It's continuous. They're continuous. There's no restricted values of x here. Okay, the domain is not restricted. All right, so those are met. Yes, we know that they're met. We draw a little graph there. Okay, so at what point is the slope of the tangent line equal to the slope of the secant line connecting f of 0 and f of 3? So f of 0 would be right here, f of 0, and f of 3, so this is going to be, let's just make this 3 out here, and this is going to be f of 3 right here. 0, 3, f0, f3. Okay? So the secant line connecting these 2 points would be this line that's drawn right through here. Okay? So how do we find out what the slope is? Well, here we go. This is the slope of the secant line. Okay, so that's the first thing. Let's check that out first. So f of 3 minus f of 0 over 3 minus 0. F of 3 is, well, now we look at the function and we plug 3 in here. So 3 cubed is 27. Minus 0 cubed is 0. over 3 minus 0. That's 27 over 3, or 9. So the slope here is 9. Are you with me on that? Does that look good? Did I make any mistakes there? Okay, so 9. All right. That's not our answer yet. That's not our answer. But what we're looking for is there some line that's would be parallel tangent here? Would be a parallel tangent? Sure, right about maybe here, I'd say. Come on. Nope. Right about here is going to be a parallel tangent line. See that? That's going to be parallel. But where is that exactly? So we are looking for this. This is C equals, we don't know what. Now, if we go back here, now I focus on this side, F prime evaluated at what C? So I need to take the derivative of this and let the derivative with the unknown value x equal 9, right? So the derivative is going to be 3x squared, and that's an expression for the slope, right, of the tangent line, and I need to know what x value yields me a slope of 9. So it honestly couldn't be easier. Find the slope of this line, then find the derivative and let that expression of the derivative equal your given slope, or the slope that you determined. So this is what? X squared equals 9 over 3. So x equals square root of 3. You might say, hey, what about plus or minus 3, Mr. Maxwell? Well, yeah, minus 3 or negative root 3 would be over here. That would be parallel, but it's not in our interval, right? It's got to be from 0 to 3. So we'll reject the negative value here. Okay, so we'll do the positive root 3. So the square root of 3 is going to be C. So C is the square root of 3. Okay, so talking a little bit more about differentiable, good question. If it's continuous and it's a polynomial function, then it's differentiable. If you have absolute values, okay, you could have like an absolute value of something, right? Like let's say you have, this is your graph, right? Well, the absolute value of this graph would look like this. It would be a nice smooth curve. This would mimic this. And then it would pop to this. See that? So it would be the black curve. Now, this would actually be a sharp corner here. This is not a smooth curve. So if you had some kind of absolute value of a strange function like this, then you would say, hey, this spot is not differentiable. So absolute values you want to be careful with. If the interval was A to B over here, you're probably fine, right? You're fine. So you have to use your brain a little bit. Maybe you might have to sketch a little bit. You might have to, on the AP exam, you probably won't get graphing calculators, so you can't just throw a graph on it. You have to use your head. If you got 1 over x minus 3, right? Or 2 or something. You know you have a restriction here at 2, right? That's going to be positive 2, right? It's going to be something like this, right? So it's not differentiable here at positive 2. So you cannot invoke this theorem. So things like that. Most of the questions will be continuous and differentiable. Because as soon as it's not continuous or differentiable, you can't do the rest of the question. So they're not going to give you a whole lot of those, right? But they might try and snag you on one of them. You know what I mean? So if you have absolute values, if you have restricted values, square roots, rational functions, those kind of things, you got to be careful that make sure it's continuous and differentiable. No sharp corners. Absolute values might give you that. And, no endpoints, right? Or, yeah. Okay, good. Let's do another one. Let's do another one. I tell you what, I'm going to let you guys attack this one on your own. Okay, I'm going to give you 5 minutes to do this, and see if you can do that. So this is what it says. It says let f. I'll just leave it up on the board if you want to. You don't have to write it all down if you don't want. But oh goodness, I think I'm missing a bracket. Let f be the function defined by f of x is x cubed plus x minus 4. What is the value of c for which the instantaneous rate of change of f at x equals c is the same as the average rate of change of f over the closed interval of -1 to 3. So this is just another way. I wrote this a different way. So you could see, if you read this on the AP exam, don't go, oh my goodness, we've never seen anything like this before. No, it's not true. Here's the function, right? Let me see if I can do that a little bit better. Here's the function you got. Excellent. What's the value for c for which the instantaneous rate of change? Oh, instantaneous rate of change, that's the derivative. Okay. of f at x equals c is the same as, boy, this is shaping up to be average rate secant line of f. Good. This is your mean value theorem. Okay, go ahead. All right, so you might have set it up this way, you might not have. This is the way I did it. Okay, I used my original formula right here. Let's try to highlight that. Original formula for a mean value theorem, okay? And then I did the derivative. I took the derivative and left the c in there. And then I evaluated the average slope here between the f of b minus f of a over b minus a. And you come up with a c value. So this is the x value that would have the same, that would have a tangent line with the same slope. So we sketched it out here on our graphing calculator. It's tough to see, but you have something like this. And here is your secant line from here to here. And root 7 is about right about here, so that is the x value that gives the parallel line for its tangent. Okay, here's another one for you to try. Again, mean value theorem states that if you have some kind of average speed on a trip, there will be at some point on your trip where you're going exactly that speed. You'll be going other speeds too. But this is a question you can answer with this. So if Jimmy is traveling to the beach at an average rate or an average speed of 24.8 kilometers per hour, the question is there a time that he is going exactly 24.8 kilometers per hour? Explain. So there's not a lot of calculation in this one, but you want to think this through. Of course, you would have to start with the hypotheses, right? So is this a continuous function? By nature, in order for Jimmy to go speed B, he has to first go speed A to get there. You cannot go instantaneously from 0 to 100 kilometers an hour, right? You have to hit all the speeds in between. So by nature, this is a continuous situation, continuous function. Awesome, okay? Are there any restricted values, any absolutes, square roots, rational part of this? No. No, it would be a smooth increase and a smooth decrease in speed throughout. Okay, it could be sharp, but it's not going to be a corner or something like that. So it is also differentiable. So because H1, right, it's continuous by nature of the problem, okay? And you could expand on that. Jimmy would have to pass through all speeds to get to another desired speed. Okay, that's one way to put it. You can't jump. Is it differentiable? H2, it's differentiable, yes. Differentiable. Okay, and then again, just by nature of the problem, there's smooth curves in graph, okay? You could say. There is no instantaneous abrupt large-scale changes in instantaneous rate. Okay, it has to be. It can be quick, but there's going to be no corners or cusps, right? It's got to be smooth, right? It's got to be somewhat smooth like this. So this is good. This one is not. Okay. Yeah. If Jimmy has an average rate of 24.8 by the mean value theorem, it means that no matter how he spent his time in between, like this, or really fast and then slowed down, or really fast and really slow and then really fast again. At some point, there will be a point on all of these options where his instantaneous rate of change will have to be equal, okay, to his average. So by the mean value theorem, at some point in his trip, he would have to be going 24.8 if that is indeed his average. A lot of speeds would be above, a lot of speeds would be below, but there must be at least one time where he's going 24.8, okay? So you'd have to think through that and explain that rationally as well. All right. Here's another way to put the same kind of question. So I'm giving you all sorts of looks at different ways to ask the same question. So I'll read this one, then I'll give you guys a chance to take a shot at it. What is the equation of, the secant line? Oh, actually, I'm asking you for an equation now, so I'm stepping it up a bit. An equation for the secant line through F1 and F3. We talked about equations last day, right? Remember that? Brought those back. for this function on the interval 1 to 3, and the tangent line on the same interval parallel to the secant line. Now we do have a -1 here, so you're going to have to check to make sure this is even possible. Okay, discuss it amongst yourselves as you work through it to help each other out. Let me know if this can be done. All right, so this turned out to be a little bit of a tough question. I'll give you that. I'll go through your answer, and if you didn't get this, that's okay. But this was a bit of a tougher question than I had planned for you at the end of the day here. But so here's how it goes here. Yes, the answer is that this is differentiable and continuous on this interval. There is a problem with x equals 0, but x equals 0 is not on this interval, so we can go forward. So we have to find the slope, okay, the slope between f1 and f3, and that turns out to be 29 over 3 is what I got. All right, use a decimal, that's totally fine. The equation of the secant line would then be y minus y1 equals m times x minus x1. I used this point and this coordinate, x and y. I put those in here. This is what I got for a secant line, an equation for a secant line. Now here's the graph in red, okay, of our original graph. And this point, this line, sorry, connects 1, -3, and 3, and 29 over 3. 38 over 3. 49 over 3, yeah. Okay, so it connects those 2 points. All right, so this is the legit. That's the answer for the secant line in A. All right. Now B. B got a little tricky. You probably wouldn't be able to do it without a graphing calculator. All right, so what we need to do here is find the derivative of the original function, which turns out to be this right here. When I let that equal the slope, remember this is the slope of the original line, it's got to equal that slope, I need to solve for C, and I actually get a cubic function. So there's where your problems might have come into play. How do we do that? Well, without a graphing calculator, you might be a little stuck, but with a graphing calculator, you graph this right here to find the solutions for this equation right here. Okay, so you bring everything over, and you're finding the solutions to this. So the solution here, or the x-intercept for this equation right here, would be 2.145. Okay, I just took a little snapshot of my Desmos graphing calculator. So C is 2.145. If that's the case, if that's the x value, I need to find the partner y value because I need an equation. So plug in 2.145, I get y equals 6.871, and I use those two values. So right here I use 6.871, and I use 2.145, and I use the slope to get this equation of the tangent line. And where did I do it? I think I graphed it somewhere. Oh, maybe I didn't put that down here yet. Let's see, Control V, yeah, there we go. So here is the blue, is the tangent line, and this right here, it doesn't show up, but this is your x equals 2.145 right here, 2.145, that's the tangent point right there. Okay, so there's your answer for B. That was a little more complicated than I had planned. It's a little bit more involved question, but there it is. All right, so here are your questions from the Finney text. It covers the last couple days that we've done here, so jot those questions down. Talks about intermediate value theorem, Rolle's theorem, mean value theorem, and we'll talk tomorrow about the extreme value theorem, which is an easy one. So here's your textbook questions.